This is a recording for pre-calculus, and this is 7-6 linear programming, and we want to be able to solve linear programming problems and use linear programming to model and solve real-life problems. So we've kind of had a little exposure to this in that last problem, and we will be looking at that problem again. And in that one, we kind of decided what the variables were, and we found some inequalities and graphed those. And now we want to kind of just expand on that a little bit more and find kind of a maximized or a minimized value as we look at that. So this is linear programming, and we're going to use a graphical approach. So we're going to have inequalities that we're going to graph as we go. And many applications in business and economics involve a process called optimization, in which you find the maximum or minimum value of a quantity. And that is called linear programming. The two-dimensional linear programming problem consists of a linear objective function and a system of linear inequalities called constraints. So you do want to know there, you do want to know that. And so this is called, we're looking at optimization is the name of that. And this strategy we're using is linear programming. And so we have a linear objective function and a system of linear inequalities called constraints for this type of problem. And the objective function is something that we're going to either maximize or minimize. So the objective function is either going to be maximized or minimized, and the constraints determine the set of feasible solutions. And so the feasible solutions in this case are all within this kind of boxed area, bordered by a bunch of things that are constraints. And so the objective function is generally z equals ax plus by. And the feasible solutions are all in this region. We're going to find that the optimum value is going to be at one of these vertices, and we found vertices in the last section as we looked at things. And since we're doing this graphically, if we write careful graphs, a lot of times we can find that point of intersection on the grid, or we can solve a system of equations to find that as well. And so every point in the shaded region satisfies the constraint, but we want to find the optimal solution, and it must occur at one of the vertices. So that means to find the maximum value of z, test z at each of the vertices. That's kind of how how we're going to approach this. So here's our general way of solving this, the optimal solution of a linear programming problem. If a linear programming problem has a solution, then it must occur at a vertex of the set of feasible solutions. If there is more than one solution, then at least one solution must occur at such a vertex. In either case, the value of the objective function is unique. So you might want to write some notes about that and pause this just so that you can go through that. Linear programming problems can include hundreds and sometimes even thousands of variables. However, in this section, we're just going to look at two variables problems. So that should be good news for you. So we're learning that process and these relationships. You know, computers can do a lot of the computation for us in the end. Okay, moving on. Here is our now guidelines for solving this, and I add a letter A there. So the first thing you have to do is decide what the objective function is and the inequality. And truly, even before that, you have to decide what your variables are and what they're going to stand for. Once you've done that, then you're going to use these three steps. First one is sketch the region corresponding to the system of constraints. So we've practiced that already. The points inside or on the boundary of the region are feasible solutions. Then we find the vertices of the region. Sometimes we can do that by inspection. Sometimes we'll solve a system of equations. And then 3 is to test the objective function at each of the vertices and select the values of variables that optimize the objective function. You'll notice they're saying the word optimize because sometimes it'll be a maximum, sometimes it'll be a minimum as we look at that. And then for a bounded region, both a minimum and maximum value will exist. For an unbounded region, if an optimal solution exists, it must occur at a vertex. And so if it's unbounded and goes like, in one direction, sometimes it might not have a minimum or it might not have a maximum, but it'll have the opposite one, so to speak. So pause this if you would like to write some things down, and maybe I would encourage that. And then we'll move on and look at our first ones. We'll just look at these in a very non-problem oriented way first, just to kind of get through the process. Okay, moving on. Ask me for some handouts. I hope that I will remember to print out some handouts. I just feel like, and I don't even know that you want to use these graphs, but maybe I'm not even going to provide the graph paper for you because you have graph paper that might be just as good to use. So sometimes when I photocopy these, they don't turn out that great. So here is number 1, and you should have the problem in front of you so you don't have to copy it all down. Find the maximum value of z equals 3x plus 2y, which is the objective function. So x and y are our variables. Z is just going to be, a value we get when we put certain x's and y's in. Subject to the following constraints. X is greater than or equal to 0. Y is greater than or equal to 0. X plus 2y is less than 4, or less than or equal to 4, excuse me, and x minus y is less than 1. So just a note to self, and we'll start just by graphing these, what we can right away. If x is greater than or equal to 0, that means that we can put this line at x equals 0, and if it's got to be greater than or equal to 0, then we're going to shade out this way. Excuse me. And if y has to also be greater than or equal to 0, when we draw that constraint in here, just a second, we're going to have y equals 0, and then they're saying y has to be greater than or equal to 0. So that's going to be here. So really what that means to me is that we're going to use this first quadrant as we go. So those two just give me all values in that first quadrant. So sometimes I take off some of that, or maybe I can make it a little more transparent so that it's not taking up my space as I'm trying to graph those other constraints. So, so those just tell us that we are in the first quadrant. And then we'll just go through our process with these other two as well. So we have x plus 2y is less than or equal to 4. And so that's going to be solid. All of these are solid lines, it looks like. And we're going to use x plus 2y equals 4. 2y is negative x plus 4. Y is negative a half x plus 2. And so we'll plot 2 there, down 1 over 2, I'm going to just find a few points here to help me draw my line. This is going to be a solid line again. And when I try my favorite point, which is 0, 0, I'll check 0, 0. In the original, I'm going to get 0 is less than or equal to 4. 0 is less than or equal to 4. So that means when I shade here, I'm shading below. So I just made my region now into this very small triangle as we look at that. That I'm looking at as we go. And our next constraint is our x minus y is less than or equal to 1. So, and that is going to be a solid line as well. And so we're going to have x minus y equals 1, negative y equals negative x plus 1, so y equals x minus 1 for that one. And I'm getting kind of to be in a small spot here, but we'll just kind of manage with it as we go. And so I'm at negative 1, and my slope is 1. So I'm just going to plot some points here that make it easy for me to draw that line. Oops, I made a little smudge, which is not one of my dots. And then I'm going to draw that in as we go. And I'll again try my favorite point. I'm going to check 0, 0 because it doesn't go exactly through there. And then when I check 0, 0, I get 0 is less than or equal to 1, and 0 is less than or equal to 1. So we are going to include that. So I'll just kind of put that there as we go. And I'll make that a little lighter as well. So our region that we're using, and I've got a lot going on here, is just right in here as we look at that. And so that's our shaded region for this one. And you know, I kind of feel like I can visually find those points, and if I'm careful. This one up here is 0, 2. This one here is 0, 0. This one is 1, 0. And this one is 1, 2, 1. And this one is 2, 1. And so that's why you want to use graph paper and kind of really do the best you can on those graphs. So those are my that's my feasible region kind of in black there. And my vertices that I'm going to be checking then are when the objective function I'm going to use is z equals 3x plus 2y. And so I'm going to write that over here. I'm going to maybe move it just a little. And then I'm just going to write down what my vertices are. I have 0, 0, I have 0, 2, I have 2, 1, and I have 1, 0. So those are my vertices, and then I'm just going to find the matching z values for those. And so z equals 3 times 0 plus 2 times 0, which is 0. Z equals 3 times 0 plus 2 times 2, which is 4. Z equals 3 times 2 plus 2 times 1, which is 6 and 2, which is 8. And z equals 3 times 1 plus 2 times 0, which is 3. So always go back and make sure you know what you're finding. So this is a maximum value. And we do have to actually go through and give a very direct statement about our solution. So here my statement is going to be the maximum, and we want to say that so we realize what we were to find. The maximum value is 8, and it occurs at the point 2, 1. In this case, we just give that as an ordered pair. You know, if it were a situation where we knew what X and Y were related to a problem, we would want to put that on there as well. So I have some slides that follow. This is probably the one that I'll attach there because of my file space on the Yola site. Here's just working those out. I'll just let you see that. And they wrote it when X equals 2 and Y equals 1, but the ordered pair is fine for me. Now, this slide just says, you know, you could try other interior points, but notice none of these are as big as 8. 13 halves is only 6.5. And so the maximum is happening at a vertex. And to see why the maximum value must occur at a vertex, think about the objective function and kind of writing it in slope-intercept form. And so if we have z equals 3x plus 2y and we get y alone, we get negative 3 halves x plus z over 2, where z over 2 is the y-intercept of the objective function. And that makes a family of lines with a slope of negative 3 halves. So there's another graphic here. And if those slopes are all kind of put along there, then you can see that along that rightmost black line, the z is equal to 8. And so that's going to occur at that vertex. Just a little, you know, deeper understanding of how that relationship occurs with that maximum or minimum based on the picture that we get. So now we're going to just try another one and see what happens. We're going to minimize this function. So z equals 5x plus 7y, where x is greater than or equal to 0, y is greater than or equal to 0, and it's subject to those constraints. And so just make sure that you write for yourself a little note that this is the objective function, because I may ask on the next exam, what is the objective function? And you actually have to pull that out of maybe a problem or a situation. And these are called the constraints, and it says constraints right there as well. So for this one, we need to graph these constraints. And so we'll go ahead, and if you want to try that, go ahead, and then we'll kind of look at what happens here and see what happens. Okay, so in this one, I know I'm in the first quadrant because x has to be greater than 0 and y has to be greater than or equal, excuse me, greater than or equal to 0. So I'm just going to think of my axes as a boundary, and I'm not even going to shade beyond those. And then I'm actually going to kind of also try to keep in mind my boundaries as I add boundaries to kind of shade a little more right to where I want to be. So let's see what happens here. And first, I'm going to use 2x plus 3y is greater than or equal to 6. And when I do that, I change it to an equation. I get y alone. So y equals negative 2/3 x plus 2. So I've got my y-intercept of 2. I'm going to go down 2/3. And I'm just going to draw that little piece because I know those are boundaries. as I look at it. I'm going to try my favorite point, 0, 0. Is 0 greater than or equal to 6? No. So it shades out that way. The next constraint, 3x minus y, is less than or equal to 15. And so 3x minus y is equal to 15 is what I'm going to graph. For this one, negative 15 is not on my graph, so it's not easy for me using this grid paper to graph that point negative 15 and use a slope of 3. So I can always use the strategy of picking an x value and finding a matching y. So I'm going to pick something that, you know, if I put it in here, it's going to be on this graph. And I think if I pick 5 for x, y will be equal to 0. And then the other one that I just picked, because I could use my slope now, from 5, 0, but I just decided to pick another value, and I picked 6, 3. So then I graph those, and I draw in that line. I check my kind of favorite point, which is 0, 0. Move that up a little bit. And is 0 less than or equal to 15? Yes. So that's going to shade kind of this way. And look at how I'm shading that. Like, you know, I went a little over that line because it's a little hard for me sometimes. But I'm kind of keeping in mind that that is a boundary as well. And so then the next thing I did is this one, and y equals x plus 4. I plotted some things there, drew my line, check my point 0, 0. Is 0 less than or equal to 4? Yes. So that's going to shade below. And then notice I'm just kind of bounding it right by those regions that I have already. And then my last one, I have kind of gives me a little more trouble. I'm going to pick an x and find a y. So I'm just going to pick x equals 1 because I noticed that 27 fifths minus 2 fifths is 25 fifths, which is 5. So I get 1, 5. And then for this one, I'm just going to use the slope of negative 2 fifths just to kind of show a different way to do that. And so I'll plot those 2 points. Notice also that those points are on intersecting points of two of the other regions, so that's of interest to us. I'm going to check my 0, 0. Is 0 less than or equal to 27? Yes. So this time when I shade, I'm kind of shading, oops, right in that little area region to kind of give me what that is. So I think that I can find these values just by inspection, and because I've done a pretty careful job. So this is 0, 2. This one is, it looks like 3, 0. This one is 5, 0. This one is 6, 3. This one is 1, 5. And this one is 0, 4. So those are my values that I'm going to check with my objective function. And so that's kind of my next thing to do. And so I'm going to remember my objective function, which is z equals 5x plus 7y. So z equals 5x plus 7y. And I'm just going to try all of these points. I've got 0, 2. I've got 0, 4. I'm going to go up and around. I can't see mine, but I have a picture here that I'm using. 1, 5, 6, 3, 5, 0, and 3, 0. So go ahead, put those in and find what we were asked to find was the minimum value. So go ahead and try that, and we'll see what you get. So let's see what you got for that one. We find that the minimum value is 14 and it occurs at 0, 2. And so that is that one. Now, I am going to just add one more problem here, and there was kind of that whole minimum and everything. Suppose it was this exact same situation and we were asked to find the maximum. And so we've done all of the legwork for this, and I'm just going to paste on my z value. So here they are, the exact same everything, but now we would just say the maximum value because that's all that is different in this one. The maximum value is, what is the maximum? 51, and it occurs at 6, 3. So just, notice that makes that pretty straightforward as we go. And kind of there's another picture of that. So it is possible for the maximum or minimum value to occur in two different vertices. So just kind of keep that in mind. Here's just a illustration of that. The maximum, notice, is at 12 for 2, 4 and for 5, 1 in that one. And so when that happens, then any point along that line segment is going to give you 12. And so there are many different solutions for that problem. Then it just kind of goes through that a little bit. And it also mentions that maybe there aren't any optimal solutions if the region is unbounded and kind of keeps going on, then there might never be a maximum, so to speak. So this is going to be maybe an unbounded region. Go ahead and try this one, and then we'll see how it went in our next recording. And this will conclude part 1.